It's time for our second talk for tonight. And we're not only in the Open Value Office here, we're also in the Yoink office, which is where Paul works. Paul Noorland has been playing with Kafka and streaming data for approximately 100 years. And he's here to tell you everything about the inner workings of Kafka Stream. So please give it up for Paul Noorland.
Yeah, thank you very much for the introduction. So first of all, let's also start with a round of questions. Who of you knows Kafka here in the room? Okay, fortunately quite a few. Who of you knows Kafka Streams? Okay, fewer, but fewer. Who of you knows how it works? Okay, two. And who of you knows how it works inside? So what happens actually under the stream, underwater? Okay, one person. Okay, so yeah, I have worked with Kafka Stream for about 5 years now. And every once in a while, when something didn't work as expected, I needed to go underwater to see what actually happened there. And yeah, that gave me kind of a picture of what happened, but it wasn't a complete picture. And then a while ago, my curiosity got the better of me, and I decided, well, I want to get to know what actually happens inside, so the inner workings. So that's what we're going to discuss today. I made an overview of that, how it works. And also of the things that can go wrong. So the undercurrent of the stream that can drag you away and yeah, cause your application to work differently than you expect. So first of all, what is Kafka Streams? Well, Kafka Streams is an event streaming framework. So you can use it to make a pipeline, a streaming pipeline. And it's a client library. So it isn't on Kafka. It is really a library for your applications. Where you can build applications that both consume data and produce it. So when would you use this? Well, it is mainly used for event-driven architectures, and it is used when you need highly scalable processing of data. So in the thousands or hundreds of messages per second. It's also quite useful for stateful processing because regular Kafka doesn't handle this. Kafka Streams has this inside of the client library. And it is very suitable when you want to combine multiple streams or multiple data sources, and you're not only producing or consuming from one topic. So this is a very simplified version of an application that I worked on. It's an application in Rabobank which shows or sends alert data to people. So at the top you see the transactions that come in. Those are the financial transactions that people make. And you see 5 streaming applications. So the top application is an adapter, which kind of takes the correct fields from the transaction. Then we had a triggerer, where we combine it with other records from the alert settings topic. And there you can do a join. So you can join multiple alerts together, and then you can forward that data again. We send it then to an enricher, and the enricher split it up into email alerts and push alerts. And this system worked for about 1 million users. So we had 1 million alert settings, and we handled about 30 million transactions per day. So it was quite a powerful streaming pipeline. And nowadays I still use it because I'm a customer of Rabobank as well. It arrives in a couple of seconds, so it's quite fast. So why use Kafka? Well, as I said before, Kafka can handle very high data volumes and also at an extremely low latency. So that's very beneficial for your users. And it has fault tolerance built in. So when it fails, it can start up again, can handle that event again. And it's all handled for you. You don't need to program that yourself. Also, it handles scaling very well, both vertical and horizontal scaling. And it is processed in real time. So no batches, but the event arrives, it's picked up immediately and processed. That's why those pipelines are so fast. So what then does Kafka Streams offer? Kafka Streams, on top of that, you can combine multiple of these data sources. Also, vertical and horizontal scaling are built inside Kafka Streams. You can manage that quite easily. And it offers exactly once processing, which is really powerful because then you can make sure that an event that you're sending only arrives at your customer, which in case of financial transactions is quite beneficial for the users. It can handle state for you, which can be really a pain, but Kafka can restore state and actually be very fast with state. It can handle the restarts, also restart of states on different machines. And it has actually a quite easy domain-specific language which will feel familiar to Java developers because it looks quite a bit like Java streams. So what does that look like? I hope this is readable for you. So I've built a very small streams application here, and what you can see on the top is something called a table. I will discuss that in later slides. But what a table does is it aggregates a number of alerts, in this case questions, and you also see a stream which gets answers from users. So what we are doing here is we start a stream, and you can see that the stream has a key, which is a string, and the value is the answer. And then you can do a couple of functional programming steps on it. So the first step that we take is we check if the ID of the user is blank. If that's not the case, then we continue. Then we map it, so we only get the answer. And then we do something interesting, which is a join. So then you can join multiple sources, and we join it based on the key. So if that answer key is the same as the question key, then we will find the event. And in that case, we can check if the answer is correct. And if it's correct, we will forward correct. If it's not correct, then we will forward incorrect. And that's basically our stream. And then in the bottom, you can see that you can send it to a new topic. So that's how you can create what we call a topology. And this actually scales very well. You can handle thousands of messages with this over multiple machines. And that is all done by this Kafka Streams framework. So back to Kafka, because I saw most of the hands going up, but it's always good, I think, to have a little of a recap on what Kafka actually does. So Kafka is a distributed messaging system, and in general, you have a producer which can send data, and the producer sends it to Kafka on topics, and a topic is a logical place to send data to, and it consists of a distributed commit log. You can have multiple topics, and applications that then read from these topics are called consumers. And these applications subscribe to this topic, and then they can pull the data from the topic. So what does this look like? As I said before, it is a distributed commit log, so it's a commit log over multiple machines, and it has a retention time. So that means that after a certain while, this message will be deleted, and the messages are on a partition. So you can have multiple partitions, and you can only add a message to a partition. And that's what you see there. You have partition 0, 1, and 2, and messages are only appended to the end, which also means it's immutable. And a topic can consist of 0 or as many partitions as you'd like. And the retention time says how long you want to keep this data on the partition, because you do not delete it after reading it. But you can set, for instance, a retention time of a day, which means that the Kafka broker will delete the messages on the partition after a day. So what does a message actually look like? Now, a message or event on Kafka is called a record, and a record consists of byte arrays. So it's quite simple and straightforward. It has some metadata in the form of headers, for instance, a timestamp, but the most important part is the body, which has a key and a value. And the key is mostly used to determine where to place the record, and the value is actually the body that you as a programmer are interested in your application. But the key plays a very important part because the key determines on which partition you eventually put your record. So the partitioning is actually quite simple. There's an algorithm. It takes the hash of the key, and then it does a modulo on it with the number of partitions. And using that, it will always, when you use the same key, end up on the same partition, which is convenient because then you also know that everything is on the same place, which allows you to make certain assumptions. We will go into that later. So if you put this together, you get a system that looks approximately like this. So you have your producers on the left, you have Kafka in a cluster in the middle, because often you have multiple instances of Kafka working together, and you have a group of consumers on the right. Another thing that is important is to notice that consumers push data to Kafka, and producers push data to Kafka, and consumers pull data from Kafka. So Kafka itself does not initiate that, And you have zookeeper, which has some of the metadata, for instance, ACL, number of partitions, etc. Another important thing is that consumers work together in groups. That's how you can distribute the workload. So what you see here is you have a topic with 4 partitions, and we have 2 consumer groups. The first consumer group has 4 consumers, and each consumer gets 1 partition. That's the maximum number of consumers per partition. There can only be 1 consumer reading from a partition. And in this case, it's satisfied. In consumer group 2, you see there are only 2 consumers, and then they both get 1 partition. So that also determines your scalability, because if you have 5 consumers, then one of them will be idle. So that's an important design choice to make when you determine the number of partitions. Then these consumer groups, they start reading from the topic, and they read per partition. And a partition has something, a partition has something called an offset. And each record has its own offset. And the consumer groups, they know from which record they have read. And then they can say, for instance, I have read up until offset 10. And then they know that the next message that they need to read is 11. What they do is the consumers, they pull this data from the topic. They process it, and then they commit these offsets, which means that they store where they have up to where they have read on Kafka itself, which is very important, because then if it goes down or another application spins up, it can join the consumer group and it can start processing from that point on. So this is a very important part in the fault tolerance of Kafka. So back to Kafka streams. Because Kafka streams builds on top of everything that a normal Kafka consumer and a Kafka producer can already do, but it's kind of like Kafka on steroids. So what you build with it is a streaming application. And in general, a streaming application does not only produce or consume, but does both, because in that way you can create these pipelines that consume the messages, start processing it in some way, do some transformations, and send it forward. And it's also suitable to do this from multiple sources. So basically you can create a data pipeline with multiple applications that read from multiple topics and produce the multiple topics. And you can also do this in a stateful way. So you can make certain counts or aggregations, etc. So how do you do this in Kafka streams? Well, it actually uses a programming paradigm called data flow programming, which is a paradigm in which you have a series of inputs, in which you do a certain transformation or a couple transformations, which produce a certain amount of outputs. And Kafka does this by creating a direct acyclic graph. In Kafka terminology, this is often called a topology, and a topology has certain processors. So the processor reading from the topic is called the source processor. Then you can have as many processors in between as you want. This can be a filter, a map, etc. And then eventually it ends up in the sync processor. And the sync processor sends it back to Kafka again, or can send it, can put it in a database, for instance. But there basically it stops, the stream stops. And each node in this case is called a processor node. And then within this you can have multiple sub-topologies. So a topology is one of these acyclic graphs, but you can also have multiples. Can also be in the same application, but often it makes sense to put these in different applications. And in this case, you see one which has which receives Slack notions. It then checks if it is valid, and if it is valid, it sends it to one topic with valid mentions. If it is invalid, it sends it to another topic. So that's also why, because it sends it to Kafka and then starts reading from it again at another point. That's why this is split up in 3 subtopologies. And what is important here to notice is that those are executed independently by the service. So each of these 3 topologies are on their own, basically. And the data moves through it in a depth-first fashion. So Kafka pulls in a batch of these records from the topic, and then each record from the topic goes through the whole topology, and then, for instance, is sent to Kafka again, and then it starts processing the next one. So that's basically how these events move through this acyclic graph. So how is this called? A couple of terminology. So actually a stream task is what runs such a topology. And per topology, a topology is instantiated per task, and it's kind of the smallest smallest units of work. So that also means that you can only parallelize as much as you have tasks. And each task is created per partition. So that's why I said before the number of partitions is important, because that means that if you have more partitions, you can scale up higher. And each task has its own copy of the processing topology, and it runs this independently. So that means you also don't have interactions between data from different topologies, which means you don't have a couple of problems that you normally have with multi-threading. And each task is then run by a stream thread. This sounds a bit fancy, but actually a stream thread is just a Java thread. You can have as many as you want. You can set those by the number of stream threads. That's a property, but often doesn't make sense to set this higher than the number of cores on your machine. And it is limited by the number of tasks, because if you use more stream threads than task, each stream thread has at least one task, else it will be idle. So that is kind of the max horizontal vertical scaling that you can get with this. So how would that look like? If in this case we have 4 partitions, which means from the source topic, which means we have 4 tasks. And if we set 2 threads, then we will see that the left stream thread has 2 tasks and the right one has 2 tasks. It has one consumer, which then pulls the data from these partitions and it divides it over these tasks. So all the data from partition 1 goes to the first task. All the data from partition 2 goes to the second task, then goes independently per record through these topologies and will then be produced to Kafka. And if you want to scale this up with 2 more threads, then you now see that Kafka streams automatically gives one task per partition, so it scales that up automatically for you, and it then has one task per stream thread. So as I said before, Kafka can also handle state for you, and you can do 2 types of processing with it, stream processing. The first one is stateless, which is a bit easier. Stateless means that you don't depend on other events. So you have one event that you process per time. It can be a filter, can be a map, can be branching, whatever, and then you forward it. The other one is stateful, which means you do care about other events. And that is, for instance, when you want to do an aggregation. So a count can be an aggregation, but you can also do a reduction there. Can be anything that you fancy, or a join. And a join is when you want to combine multiple data sources. And something that is important there is something called a compacted topic. So with the other topic, we deleted the data when a certain time passed, which was called the retention period. But in this case, we overwrite the latest key in that topic. So in this case, we see a couple of keys. It ends with K5, K2, K2, etc. And what you see is that when the log compaction takes place, we only keep the latest key. So you can see that, for instance, for K2, we only keep value 3, and value 2 is thrown away. This is quite convenient, because in this case, you can make, out of a stream of events, you can make a table out of it, because then you keep only the latest version of that key, of that event, which for instance would be the latest state of a machine, or in case of the alert from Rabobank, the latest alert settings from a certain user. And you can use this to join with other streams and then to combine the 2 values based on their key. And state is stored in Kafka in something called a state store. So a state store is kind of an interface. It's a logical abstraction. And what it does is, it is created for a stateful operation. So when you have a stateful operation in Kafka, for instance, an aggregation or a count, underwater it will create this state store where it stores all these alerts in a similar fashion as I showed. So it keeps the latest value for that key. It is created, for instance, when you make a k-table. K-table is that table abstraction that you can use for a join. And you can use that, for instance, to enrich events. And in the DSL, you can do it in two ways. I have some water here, thanks. You can do that by defining a k-table, which is what I showed in the beginning with the DSL, or you can do that by creating an aggregate. And on the lower level, so not using DSL but going one level deeper, you can access the state store directly as well. There are two types of state stores. One is persistent and the other one is in memory. In memory is quite straightforward. It's just kind of like a map that you can use. But persistent is a bit more interesting because then the data is persisted on disk. And this is embedded per task. So each task has its own state store, which means that it doesn't need to do a call to the database or a network call. So this is much, much faster. And because it is on task level, it also prevents some concurrency problems where multiple threads are trying to access the same state at the same time. And it's basically a key value store, so you can only retrieve something based on the key, and it's backed by a changelog topic. So when you create this aggregate, it's not only on your disk, but it's also sent to a Kafka topic, which means that if your application goes down, another one can come up and then say, I want all the data from the changelog topic to fill that state again. And by default, it's stored on disk, and it's stored on a small database called RocksDB, which is developed by Facebook. And yeah, it stores it as a key value store, very fast, so very convenient for this use case. As I said, it's backed by changelog topics, and this is very convenient when you want to play back the state. So if your application goes down or you spin a second one up, which gets some of the partitions as well, then it needs to fill it up again, and it can do that using the changelog topics. It persists this on disk, and it's backed by these compacted topics. You can query it by key, and yeah, what I said before, you have a local one, so this is per thread. But if you have a small size of your topic, you can also decide to make a global k-table. So this global k-table is quite useful when you have small and static data. So this would be number of products that doesn't change that much. The best thing about that is that you don't need to change the key for that. So you can match on different values there. And this is not per task, but the global k-table is for the whole stream. So the whole stream instance has one of these k-tables. It has its own separate thread, and you don't need something called co-partitioning. Co-partitioning will be explained a bit later, but it is one of the things that you need to have the same keys on both topics, because else you will not find the same the same value. So on these local stores, you only have the data of one partition, and it's on task level. And yeah, basically the stream thread controls that, and you do need a co-partition. So co-partitioning here, as I said before, you have a couple of requirements, because if you have your stream task, that only listens to one partition. And if you have a k-table with that partition, then if it has a different partition, it cannot find it. So yeah, there are a couple of requirements, which is it needs the key, which is the same field. It needs the same partition strategy, and it needs input topic with the same partitions. Yeah. And sorry guys. So yeah, how is this stored on disk? So this everything in here is stored on the disk itself of the application, and it's stored in a certain folder called a temp folder with Kafka streams in it, and each task has its own folder in that folder. So you have the subtask and the partition, and as you can see here, so your application is called dev consumer, and you have the different pulse counts, and for each partition you have your own folder in here. So you have, in this case, 4 partitions, which is 0, 1, 2, and 3, and each partition there has its own data, and each task has its own has its own little state store with its own data in there. So actually, how do you define everything? You define it by something called a stream builder, and the stream builder builds a topology. So streams builder is your class in Java, and based on that you can build the DSL, and the DSL is the high level where you can have the common data operations that you normally want. So those are your filter, your map, those kind of things. And if you want to go lower, because the DSL doesn't provide what you need, then you can write your own custom processors, and you can also have state store access. So there you can do something that was not built in that DSL for you. So this is the example that we saw before. I hope now it is a bit more clear for you. So here in the top you have that K table, and the K table listens to a topic called question topic, and it fills that up for you with all this partition data. And then you have your K stream, which listens to that to the player topic, and it starts consuming from there. Then you can do your stateless operations, which is the filter, which is the map values, and then you can join. And join is your stateful operation that will be done on task level. So in this case, we're using a regular K table and not a global K table. So we'll join it per task. And in this case, if it finds something, it will check the answer, check if it's correct, and then forward it to the answer corrected topic. So how does this actually work? Because we see a very nice builder, but what actually happens underneath? So as normally with a builder, if you put something on a builder, you get exactly the same thing back, and underwater it just adds it to some kind of data structure. So in this case, what it adds it to is a K-stream implementation or a table implementation instance, and every time you call it with a map or a filter or anything else, it will add a node to the internal builder, and it will then return that K-stream again. And so every method that you call on the builder will add a processor node to this builder. So this is, for instance, with a filter or a map. And what then happens is that when you start processing, it will receive data from the parent in that builder. And then that data goes to the node. That node does a certain operation on it, for instance, the filter or the map. And then it will forward it to the children. So it can have one or multiple children, and it will forward the data to these other stream nodes. There again, these notions come back from a source, a processor, and a sink, because the first one in this builder will be the source, the intermediate ones will be the processors, and the bottom ones will be the sink. And the sink also has the producer, so that in it has a regular Kafka producer that will send data to your topics again. So what happens when you actually run this? I hope this is big enough. Here you can clearly see that underwater it has created these processors. And in the top you can see it has a source processor which reads from the player topic, and it forwards it to the filter. The filter is the second one which gets it from the source and forwards it to the map, and that's how it goes down. In the bottom you see the K table, which reads from the state, from the question topic, and stores it in the question state store, and the join joins it with that state store. That's how it continues through all these things. So how do you actually start this up? This is all the code you need to start it. I've reduced the size of the streams builder and the topology to make it fit in the screen. But actually you only need a couple of configurations. Then you have your streams builder, which defines your topology, and you pass it to a Kafka streams object, and that's basically all you need to do. But then the question, of course, is how does Kafka Streams run all of this? Well, we've gone through the concepts, but now I would like to walk you through a bit of the code. It's kind of the code that they use underwater, but I've simplified some of it, so it's kind of pseudo code, because else it would be a bit too big to fit on the screen. But first of all, you have your constructor, and the constructor checks or builds a global state topology, which is when you have global state. So when you have a global state store that listens to all these partitions instead of only the one from the task. If that is there, because it can also be, for instance, the example that I showed, that you don't have the state store, the global state store, then it will not create your global stream thread. If it is there, then it will create it. So this first part, there's actually a bit of an if statement around it, but I wanted to show that you have a separate thread that is created. And in the second part, you see a for loop, and that depends on the number of threads that you've set for that particular application. And for each one, it will create its separate stream thread. Now then, if you call the start method, which you saw in the previous code example, it will call run on all these threads, which is what you know from regular Java thread. So what happens then inside the stream thread? First of all, it starts subscribing as a consumer. And when a consumer subscribes, it says, I want to have data from this topic. It gets its partitions that it needs. And then for each partition, it creates a task. Yeah. So while it's running, then it gets it does a pull request where it gets all the records. So there's one consumer that gets all the records for all these partitions, which it then adds to the tasks. So that is, before it starts processing anything. It then gets the changelog reader and says restore, which checks for all the tasks if there are state stores, and it fills all these state stores with the latest updates, which means that before you start processing any of these events, it will then be up to date. Well, then then the next part is the task manager, where you can call process. And the task manager manages the tasks. It has all these tasks, and because you assigned or you added the records to these tasks before, it will have all of those, and it will then start processing them. And then in the end, the task manager also knows up to which records were processed, and it commits all these offsets, in which case you say, my streams application has read up till this point, and it's processed. So just one dive deeper, what actually happens in the task manager. The task manager has all these tasks that I discussed before, so one task per partition, and it then calls process on these tasks. And the process, the task manager checks if the stream task still has records, and while it has that, it calls process on these stream tasks. And then it gets the next record, and because each stream task has a topology, it only needs to get the first source of the topology, which is the source node, and it then calls the process method on that first node. And then we go back to the actual code that we see. So this is what you built with that builder, and actually inside of each process node is this kind of interface. Depending on, for instance, the first one is, I think it's the filter, am I correct? No, it's a mapper. So it has a map, basically a lambda that that expects a key and a value, and it calls that map operation on it, which does the transformation, and then you pass it to the context. So you see context.forward with the new key and value, and that gives it to the next children. Can be 0 or many. And that is also a similar task like this with a process. And that basically goes through the whole topology until it hits a sink. So second example is a process for a filter that just has a predicate. It tests the predicate. If the predicate is true, then it forwards it to it. If it's not true, then it doesn't. And I think here they combined the filter not and the filter, so that's why it checks that as well. Okay, so then the risks that you can have with this with Kafka Streams. The first one that I've seen is that people do not realize that Kafka Streams uses a builder. So it's quite obvious, I think, after this story with the tasks and the stream builder, that is a builder. But some people mistake this for sequential code. So they think that because it starts with the K table, that the K table will always contain everything before the stream. And what you can also do, you can see that in the example here, is that you start a stream, you do some operation on it, like the peak, and then you start doing other operations, like the filter and the map, in a second instance. So that's how you split it up and give one of these processors two children. But because of optimization in this builder, you don't know for sure which of these methods is called first. So you need to be a bit careful there that you don't make these assumptions. And you really see it as a builder instead of sequential code that is executed. The second one, of course, is state. If you have state, then you can go out of memory. So you need to be careful with how this state is built. You have compacted topics, and they override the key. So you must make sure that if you send new keys, that they do actually override it. So if you send a UUID, or if you include the time, for instance, that will not happen. So that can be a problem. And then also your application can go out of memory, which will make it crash, of course. And the last thing is that a rebalance, so that is when you get new partitions for certain applications, will take more time if your state is bigger. So those are all things with state in Kafka streams that you need to be careful of. Then, of course, inside your builder, you can also create streams, create state. So it's important to realize which operations in this builder create state. And most of these are the aggregate types. So if you, for instance, do an aggregation or a count or a reduce, be mindful that underwater you create a topic on Kafka where you put all this data on, but you also create this state store on your local disk that accumulates all these data. Besides that, it can also be that you need a repartition. So if you change the key, then it might need to change partition as well, and it needs to put this data on these new partitions because it needs to be sure that it has the partition of the state store and it has the partition of the topic which contains the same key, because if it doesn't have that, then it will miss the data, while actually it would have been there if it was co-partitioned correctly. So if you have a repartition and you do that because of your builder, then you duplicate all the data under a different key. So be mindful of that data duplication. So key changes lead to co-partitions and data duplication. Then have any of you used schemas with Kafka? Afro schemas or something like that? Yeah, you? Okay. If you do joins, then actually, because Kafka is sending byte arrays, it will include the schema version in your key, and it does an exact lookup on that key. So that means if your schema changed from 5 to schema 6, that it will not match anymore, even though you, for instance, only have an ID which is a string, which is exactly the same. We had this at Rabobank, where they changed it from string to char sequence, which then caused the schema registry to give it a new schema number. And we had a lot of problems figuring this out, because when we were debugging it, the key looked exactly the same.
Poison pill?
Sorry?
Poison pill in Kafka?
A poison pill.
Yeah, when a message comes in, jams the whole thing.
Yeah. Well, in this case, it isn't a poison. Does everyone know what a poison pill is? A poison pill is a record in a streaming application or an event-driven system that will break the whole thing because it cannot be processed. And it depends on how you handle it, because you can, for instance, log it and throw it away. You can send it to another topic to be processed or investigated later. But in general, poison pill would kill it. In this case, it wouldn't find anything. So a join can happen where there is no other key, right? That's a very valid case. For instance, with the alert settings, if a user doesn't have settings, it won't find anything to join with. So that's a tricky situation here, because not finding anything within such a join is actually a valid case. But of course, it's a bug in your system. So be careful with schema joins. Either make sure you don't change that schema, or do as we did and do all these joins only on strings, because we did them on IDs anyway. So then you won't have these schema problems. Then exactly once. Kafka offers exactly once processing, which is really nice, but it is non-deterministic. And this might sound a bit abstract, but that actually means that if you have a k-table with certain values, of course these values can change if you receive a new message there. And especially with global k-tables, this can be a problem. So if it changes in the meantime while something goes wrong with your processing, and you start processing it again, then it will find a different value. So let's take an example. You process something, you want to forward it, but it crashes your application. Then it starts up, it fills that k-table again, the global k-table with all the new data, and it starts processing that record again. It will then produce a different record. So that's kind of the eventual consistency that you have there, that Kafka calls that non-deterministic. So they say it's a subset of legal outputs, and the legal outputs are then the outputs that you can get with the two different values in the k-table, the earlier one and the one just after the update, which then happens on that compacted topic. So the last one, which is also a nasty one, is if you change the partitions. As I said before, your partition is determined by the key. So you do a certain hash on that key, and then you do a modulo on the number of partitions. If you change the number of partitions, that modulo changes. So that means it will end up on a different partition. And especially if you use a compacted topic, it overrides the same key, but only on that partition. So it's not global for the whole table, for the whole topic. It's only on that partition number. We have that at Rabobank as well, because we changed that. Didn't realize this. And then with a global k-table, because you get the whole table, we sometimes got weird results because we got older records at some point. So please be careful if you change the number of partitions if you have tables. It will lead to data inconsistency. So that's it. Sorry for the moment of doubt in the beginning, in the middle. Do you have any questions?
The single processing guarantee. What if you have multiple sinks and only one fails? Is it retry only the one that failed?
What do you mean with multiple sinks? If you send it to multiple topics.
Yeah, and one of those sends fails.
Yeah. So actually, what happens is what Kafka does is it creates a transaction. So the Kafka broker has supports transactions. And what it does is it sends that record within that transaction. And it only commits that transaction when it has committed the offset as well. So even though the record is on Kafka, it will not have that transaction committed until the offset is there as well. And then it will mark that record as committed, which will then be allowed to be read by new consumers. So if it breaks off, and it has sent it to 2 sinks but not to the third, it will also not commit that offset. So that means that the record is kind of unreadable for consumers. It will then start reading from the sources again, process it again, send it to Kafka again, and commit the offset, and then it can be read. So that's how it makes sure that only process once.
It sounds like the two that did succeed would receive it again.
The topics, you mean?
Yeah.
Yeah, it is sent to the topics, but because it isn't marked as that the transaction is committed, it won't be read by downstream consumers.
Yeah.
So that's how they have solved this exactly once processing.
Okay.
Yeah.
Those streams, they execute on your on clients, right?
Yeah.
Not on Kafka itself.
No.
So I was wondering a little bit, it pulls its data from a partition. How much does it matter that you have multiple partitions? Isn't that a separate problem?
Yeah.
You can have,
Yeah, exactly, yeah. So, you want a good number of partitions because that offers you scalability.
yeah.
As I said before, you don't want to change that number of partitions because that can cause these problems that I discussed. And you also want an easily divisible number. because then it can be divided easily over multiple consumers. So yeah, often a number that you hear is 12 because it can be divided by 1, 2, 3, 4, and 6. But you also don't want really a lot of these consumers, because then you get, for instance, a lot of tasks or a lot of partitions, because then you get a lot of tasks and it becomes more cumbersome to handle. And especially by Zookeeper, which keeps the metadata of the Kafka cluster, and that can handle, I think, only a certain number of partitions, which is in the millions. But still, if you scale it really high, it becomes more difficult.
Okay.
So
Yeah.
But you cannot have more. So it's like not two threads cannot read one partition. It's no use because you have competition.
Yeah.
So you only have max one.
Yeah, you only have you only have one task per partition.
Yeah.
A partition can only belong to one task,
Yeah.
and a task can only belong to one thread. So it's not the case that multiple threads will read from one partition.
No.
So in that case, it's limited, but that does give you a lot of advantages on multi-threading, that you know that everything from the same partition is only there. So you need to scale it in terms of number of partitions that then are handled by individual threads. Yeah.
Yeah.
Other questions?
Yeah, but it's related, but it's not really. It's like we did distributed tracing. No, trace IDs.
Uh-huh.
They were lost in the Kafka stream.
Why?
We don't know. They're lost. So we made a workaround to get the trace ID back in the end with the producer, with the sync.
That's what your experience, you mean,
Yeah.
that you had?
Yeah, and I heard Confluent, I talked to people that used Confluent,
Mm-hmm.
Kafka, and for those work, but we use actual Kafka,
Mhm.
it didn't work, lost. So it's lost in the header.
Hmm.
No trace ID.
I don't have experience with trace IDs in headers. It might be that in the I know that the timestamp when Kafka Streams produces a new message, that the timestamp is copied. It might be that the trace ID is not copied. There might be some way that if you produce it again, that you in your Streams application that you can set that as well in the header. But yeah, I don't have experience with that.
Yeah, I didn't find it yet. Okay.
Hmm.
Okay.
In multiple stream join situation, how can we handle the late event? I know Kafka streams don't have watermark strategy,
Mm-hmm.
but in processor API, I don't have any experience. Do you have any experience about that?
You can handle it in multiple ways. One thing that we did for the alerts is we said we are not interested in anything older than 2 hours, because that is too late for a user. So you can filter that out based on the timestamp. That is quite easy. It's just a filter in that that builder that I showed you. Another thing is if you build state in an aggregator, you can do that in a windowed way. Then it checks for certain timestamps, and it has a grace period. So if you can set the grace period where you say if it's older than a day or whatever, do not edit anymore, and then it will throw it away.
Do we need to customize the late events for specific downstreams, or it's automatically managed by the DSL?
And in case of that windowed aggregation,
Yeah.
it's automatically done. Yeah, it's handled by the DSL.
Should we provide a different Kafka topic or DLT, etc., or
To throw it away, you mean?
late events for late events? Scripts or just?
As far as I know, it's dropped. It's not sent to it's not sent to a dead letter topic or whatever. Yeah.
And I have another question about the long time repartition state and rebalancing state.
Mm-hmm.
Do you have any other experience without restarting the process? Because it takes a long time and you don't have another chance. You have to restart the process to
I don't fully get the question.
I mean, for example, when any Kafka Streams application goes to a balancing state,
Yeah.
as you said, if you have a huge state,
Yeah.
it takes long time.
Yeah.
Sometimes it takes 30 minutes, maybe more.
Yeah.
In this situation, in our case, we have to restart application.
Mm-hmm.
Then Kafka Streams start again and
Mhm.
clear the state.
Yeah.
Do you have any use case in that in this scenario without restarting application? How can we manage in this it in runtime?
Well, what I know with restarting is that depending on if you store your data on your disk, then it knows until which offset it has read. So then when it starts up, it uses that same disk again, where all the data is already in RocksDB, and it only needs to read the new records that have arrived on that compacted topic. So that will greatly reduce the startup time, because it doesn't need to read the whole topic, but only the new messages. So that is one thing, and then you need to make sure that you use a persistent store and not in memory. Another thing is that you can, I've read about it, I've not used it, but you can have standby replicas, which is actually a client application that has this state store copied. Normally it's not used, but when another application goes down, it can see that that state store for that partition is already on another client, another application, and it can start using that. So then it can immediately continue streaming, and then the new application that comes up becomes the standby replica and starts filling the state store again.
You mean the session timeout and membership ID, or I didn't get it. This how can I say? You know, when it goes to rebalancing state.
Mm-hmm. Yeah.
Before the version 3, it was a stop the world. You know.
Yeah.
It have to purge all assigned partition
Yeah.
and reassign again.
Yeah.
If you have 50 partition, it takes long time.
Yeah.
But after cooperative sticky assignment protocol,
Mm-hmm.
it's better than before. But
Yeah.
still, they have a how can I say? It's not stable right now. In this scenario, you have to restart the application Kafka Streams process.
Mm-hmm.
Because it takes long time rebalancing state. I mean, do you have any scenario, because you have a lots of traffic?
Well, I know it's doing a cooperative rebalance, so it doesn't stop everything,
Yes.
but it checks actually what has changed, which partitions have changed, and then it continues processing the other ones, and then only assigns those. I don't have experience with problems that we needed to restart it. What we did is if it crashed or if it stopped running Kafka Streams, we restarted that application, which sometimes was annoying indeed. But we didn't have that much in the state stores. Plus we divided it over a couple of instances. So we had a startup time of I think 2 minutes, something like that, which was annoying. But in our case, not the biggest problem.
If you have any further
Yes?
questions, feel free to grab Paul during drinks.
Yep.
I have 2 things for you.
Thanks.
The first thing requires partitioning before consuming.
Thank you.
And the second, as a consumer, is advised to process it in a streaming manner.
Yep. Thanks.
Thank you, Paul. Feel free